Hey everyone, and welcome. Today, we're going to break down one of the absolute cornerstones of linear algebra, how to find eigenvalues and eigenvectors. And by the time we're done here, you'll have a super clear, step-by-step method that works for any 2x2 or 3x3 matrix. So let's dive right in.
At its heart, the entire process, it doesn't matter if it's a small matrix or a big one. It really all comes down to solving just two fundamental equations. If you can master these two, you've mastered the whole procedure.
And here they are. The first one, on the left, that's what we call the characteristic equation. We use this to hunt down those special numbers, the eigenvalues. We call them lambda. Once we have those values, we take them and plug them into the second equation, over on the right. That's how we find their special corresponding vectors, the eigenvectors, which we call x.
All right, let's start with level 1 of our challenge, a classic 2x2 matrix. This is the perfect place to learn the fundamental steps without getting bogged down in too many details.
We're going to follow a pretty straightforward three-step game plan. First, we'll build that characteristic equation. Second, we'll solve it to get our lambda values. And third, for each one of those lambdas, we'll go and find its own unique eigenvector.
Now look, you could find the characteristic equation the long way, but who has time for that? We're all about working smarter, not harder. So we're going to use this awesome shortcut that works for any 2x2 matrix. And this is the magic formula. Seriously, commit this one to memory. It'll save you so much time. It's lambda squared minus s1 times lambda plus s2, all equal to 0. Simple, right? But what are s1 and s2?
Well, they're actually really simple. S1 is just the sum of the numbers on the main diagonal, and S2 is nothing more than the determinant of the matrix. Let's see how that works.
Okay, so here's the matrix we're going to tackle. You can see the main diagonal elements, the ones we care about for S1, are 5 and 2. First up, S1. Super easy. Just add up that main diagonal. So 5 plus 2, that gives us 7. Done. Okay, now for S2, the determinant. We multiply down the main diagonal, so 5 times 2, and then we subtract the other diagonal, which is 4 times 1. So that's 10 minus 4, which leaves us with 6.
See how easy that was? Now we just pop those numbers S1 and S2 right back into our shortcut formula. And boom, there's our characteristic equation. Lambda squared minus 7 lambda plus 6 equals 0.
Okay, step 1 is officially done. So what's next? How do we actually get our eigenvalues out of this thing?
Well, you can get your hands dirty and factor this yourself, or hey, just plug it into a calculator. Either way, you're going to find that our two eigenvalues, our two lambdas, are 6 and 1. And just like that, step 2 is in the bag.
All right, on to step 3. The key thing to remember here is that every eigenvalue has its own special eigenvector buddy. So we got to find one for each. Let's start with lambda equals 6.
So what we do is we take our lambda equals 6 and plug it back into that second big equation we saw, the a minus lambda I x equals 0, 1. This whole thing spits out a couple of simple equations. If we just look at the top row, we get negative x plus 4y equals 0. With a tiny bit of rearranging, you get this beautiful, clean ratio, x over 4 equals y over 1. And those numbers right there in the denominator, that's our eigenvector, 4, 1. Pretty cool, huh? And now we just rinse and repeat for our second eigenvalue, lambda equals 1. You plug it in, you'll get an equation like 4x plus 4y equals 0. Simplify that down, and you get the ratio x over negative 1 equals y over 1. And there it is, our second eigenvector, negative 1, 1. And that's it. First challenge complete. Awesome job. You've totally nailed the 2x2. So, you know what that means? It's time to level up. Let's take everything we just learned and apply it to a bigger, beefier 3x3 matrix. And the good news is we've got another shortcut for this. It looks really similar to the last one, it just has one extra term for that third dimension. Notice the pattern with the signs. It goes minus, plus, minus. That's a key thing to remember. So S1 is the same as before, just sum up the main diagonal. S3 is also familiar. It's the determinant of the whole 3x3 matrix. The new player here is S2. It's the sum of the cofactors of the main diagonal elements. And a cofactor is just a fancy way of saying the determinant of the little 2x2 matrix that's left when you cross out an element's row and column. So for our example matrix, and we're skipping the number crunching here to save time, but if you were to calculate S1, S2, and S3, you'd get 7, negative 36, and negative 36. You plug those into our 3x3 shortcut, and you get this cubic equation, Again, you'd probably use a calculator to solve this one, and it would give you our three eigenvalues, -2, 6, and 3.
Okay, so finding the eigenvectors for a 3x3 matrix can get a little messy. But there's a really slick technique called the cross-multiplication method that makes it way easier. It's a clever way to solve for 3 variables using just 2 of the equations you get.
So let's find the eigenvector for lambda equals -2. Just like before, we plug it into our a minus lambda I x equals 0 equation. That's going to give us a system of 3 different linear equations. But here's the trick. We only need to pick 2 of them. As you can see here, we've pulled out the coefficients for x, y, and z from the first 2 equations. This is what will feed into our method.
Now, when you apply the cross-multiplication method to those numbers, to get the number under x, for example, you kind of cross-multiply the y and z coefficients. 1 times 1 minus 3 times 7, which is -20. You do a similar thing for y and z, and it gives you this perfect ratio that connects all 3 variables. X over -20 equals y over 0 equals z over 20.
So that ratio tells us our eigenvector is -20, 0, 20. But we can clean this up, right? You can see that all 3 of those numbers can be divided by 20. So let's just factor that out to simplify things. And that leaves us with a much nicer, cleaner vector, -1, 0, 1. And that is our final eigenvector for lambda equals -2.
Whew, okay. We have covered a lot of ground, all the way from a simple 2x2 to a 3x3, so let's just take a second and boil this all down into one universal guide that you can use for any of these problems.
Here it is, 4 simple steps. Step 1, use that shortcut formula, the 2x2 or the 3x3 version, to get your characteristic equation. Step 2, solve that equation. Find all your lambdas. Step 3, now for each of those lambdas, one by one, you plug it back into the eigenvector equation to find that vector ratio. And finally, step 4, write down the vector from that ratio and, super important, simplify it if you can by factoring out any common numbers. That's the whole game plan.
So there you have it. You've totally mastered the how-to. You've got the procedure down for calculating these special numbers and vectors. But that really just leads to the next big question, doesn't it? Why? Why do we even care about these things? What does it actually mean when a matrix acts on its own eigenvector? What's really going on there, geometrically? Well, that is the next fascinating step on your journey. Thanks so much for watching.